Okay, Calc 4, Lecture 11, Determinants, Part 2. So, evaluating determinants by row reduction. So, let me just write down some facts. I really don't want to go through that. In fact, some of them cannot, some of these facts cannot be proved easily. So, fact 1. Okay, what is fact 1? If I multiply one row of a matrix by some constant k, then the determinant is multiplied by k. So k times, say, row I, if this goes to row I, then a determinant of the resulting matrix. So this gives me, say, matrix A, say, hat. A hat is k determinant of A. So if by doing this operation I go from A to A hat, then the determinant of that A hat is k times determinant of A. Now this one is not hard to understand. So let's take A. Let me just write a 3 by 3 matrix. Okay, so when I multiply this by k, this is A, so A hat will be k. Let's multiply the first row, k. Okay. Now, what is determinant of A hat? It is k A11 times C11 plus k A12 C12 plus k A13 C13 to that cofactor expansion. So it is k basically A11 C11 plus A12 C12 plus A13 C13. So this is determinant of A, so that is k times determinant of A. Okay? So, well, I can write, it can be just any matrix, A and N, and this can be any row, then you just change A, I1, I2, I3 up to IN, C, I1, blah, 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 and each one of them is multiplied by K. So you can factor K out, and the inside is in fact determinant of A. So multiply one row will change it like this. Okay, now let me erase this thing. So this row operation is not that useful, unless, well, if you need to do that, you might say, okay, I have a matrix with lots of fractions. If I multiply rows by some number, I will get rid of the fractions. Okay, so, but be careful when you are multiplying the determinant by certain numbers. Now, fact 2 is, suppose, well, I'm going to use this fact to say something. So, this is in fact like this. If a row of a matrix can be decomposed into two parts, just one row, then the determinant is decomposed in two parts. So let me write just an example of this thing. So suppose a matrix A is like this: A11 plus B11, A12 plus B12, A13 plus B13. Then the second row is A21, A22, A23, A31, A32, A33. Now, what is the, if I just write the cofactor expansion, determinant of A will be, the cofactor expansion using this. So it will be A11 plus B11 times C11 plus A12 plus plus B12, C12. Then the third one is A13 plus B13 times C13. Okay, so this can be, if I distribute this, I will get A11 C11 plus A12 C12 plus A13 C13. And the same happens to B. B11 C11 12 C12 B13 C13. Okay. But these two are determinants of two different matrices, right? This is determinant of something, determinant of some A, say 1, say, and this is determinant of another matrix, determinant of A2. Okay? That's determinant of A1, the other one is determinant of A2. But what are A1 and A2? So, let me erase this like number 1 and write the A1 and A2 for you. You can guess by looking at this. So that A1 is in fact just A11s that's the determinant of this guy here, and then A2 you can guess that is the B. So this one plus this one is not A. I'm not decomposing A in this formula. Just put them together. These are added. All of them are added, not just the first row. But if I can decompose one row into numbers like this, say, and then I can find determinants by finding determinant of each one like this, and then adding them. So this is fact 2, which can be, the number 1 and 2 are easy to prove even in the most general form. You can guess if one row other than row number 1, if I have n by n, then this will be AI1, BI1, AI2, BI2, and so on. And you will get the same thing, except you have more than 3 terms. Okay, so this is fact number 2. Let me erase this. Now, number 3 is this. If a matrix has, if 2 rows of a matrix or 2 columns, no difference, and this also can be used for columns, but let's use it for rows. If 2 rows or 2 columns of a matrix are the same, then the determinant is 0. Now, I'm not going to prove this thing, but let me give you an example. So, if 2 rows or columns of a square matrix are the same, the determinant of the matrix is 0. Okay, so I can just write 1, A11, A12, A13, say, and let's just write the second row the same, A11, A12, A13, and the third row is A31, 32, 33. Okay, let's check. So determinant of this thing is A11 times determinant of this, which is A12, A33 minus A13, A32. Then 2 times it's minus, remember that's minus, this one minus, then times this times this, A11, A33 minus A13, A31. And the last one is A13 times determinant of this, A11, A32 minus A12, A31. Now let's look at this more carefully. In fact, this the proof is something like this. In fact, but the proof, at least the one that comes into my mind, uses a different expansion for determinants. So let's see. This is A11, A12. This one. So I have an A11, A12, A33. Let's find another A11, A12. There's another one here, A11, A12, but here A12 comes first. You see, this one is this times this, A11 from the first row, A12 from the second row. This one is A12 from the first row, A11 from the second row. This flip of permutation changes the, say, sign of this. So if this is positive, this is negative. If this is negative, this is positive. The rest of them are the same. So just those two in each one of them. You see, when you find the determinant of a 3 by 3, every one of them has 3 terms. Every, say, term here has 3 of the entries. So it's a product of 3 entries. So if you have a 4 by 4 matrix, you will get 4 of them. So if you have n by n, each term in the determinant has n entries, it's a product of n entries. And in each one of them, you can find one of these entries. You see, each one of them has one entry from here, this row, one entry from this row, one entry from this row. Just look at that. And so it has a one entry from this one, say if it has one entry from this entry and this entry, which is this term, another one should have this entry, then this entry, then something else. So you can see that these two with A33, so the third one should come from here, and it can't be these two because these two are already here. So, and there's a flip here. This is 1, 2, this is 2, 1. And that flip changes the sign, and so whatever the sign of this one is, the sign of this one is negative of this. So they cancel out. So they cancel. In fact, the proof using that, what I said is like that. So this one cancels with something here, and some of them cancel, and you can just write this down for yourself and see that they cancel out, and you will get 0. So it's in fact interesting. For some of you might be good to know that the determinant will be something like this. So it is sigma of the product. This is product of say aij's. That's the product of aij's. But this is I, then the j will be some permutation of I, which we call it sigma of I. And then I goes from 1 to n, say, and then this is multiplied by SGN of sigma. And now what is SGN is a sign. So each term here is a product of terms, entries of the matrix, each term here, and it takes 1 from each row. And the ones that it takes, if it takes this one, it won't take this one. So if it is this one, then the other one should be this one, or maybe this one, or maybe the other one. So the second index is not like the first index when it goes to the second one. So these, if it is 1, 2, 3, 4 up to n, then the second indices are a permutation of that 1 to n. That's what I wrote. Sigma is a permutation of 1 to n. and then there's something called sine of sigma. Now, those two that are the same. So this one and this one are the same, except for the sign. But since there's a flip here, this sign of this one is different. But anyway, I just gave you some idea of what a determinant is. So determinant, every term here that you see, it takes one from this row, one from this row, one from this row. And they are not in the same column, okay? So they're from different columns. So if it takes this one from this row, it won't take this and this. It will take maybe this one and say this one, say. So it one from each column, but say it can start anywhere. So it can start here, for example, but then goes backward, forward or backward, and it takes terms from the other rows without intersecting them. I mean, from each row. So there are two from one row. But anyway, so let me erase this. So if two of them like this are the same, determinant is 0. Now, in fact, for this one is crucial. This one is in fact the one that we will be using to find determinants. K times row number I plus row j going to row j. This gives me, this changes the matrix to A hat, and it's not surprising, determinant of A hat is determinant of A. This is amazing. Just this one, just this operation, which maybe I have mentioned that it is the most important operation. This operation of adding a multiple of one row to another row does not change the determinant. Now, let's see why this doesn't happen. I mean, why this happens? Why does this happen? So let me erase and use the whole board here, because this is what we will be doing to find the determinants. So let's see why this happens. So let's say I have A. Let's just write 3 by 3. So let's do this. Say K times row 1 plus row 3 goes to row 3. So this gives me this matrix A hat. This doesn't change. The second row doesn't change. The third row will be K A11 plus A31, K A12 plus A32, K A13 plus A33, right? Okay. So let's go back to, I guess that was fact number 1. This row here is like it has two terms in each one of them. So this will be determinant of, it will be determinant of this A11, A12, A13, A21, 22, 23, and this is K, A11, K, A12, K, A13, plus determinant of the other matrix A11, A12, A13, 2, 1. Okay. Remember from fact 1, determinant of that A hat is these two. Well, what is this? Well, let me, do I have some? Well, let me erase this thing and right here. So this guy here, there's a k here, right? If I multiply one row by k, that is k times determinant. So this guy will be k times determinant of A11, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, A11, A12, A13, right? So what is this? This has two rows which are the same. So this determinant is 0. 0 times k is 0. So if this guy here is 0, then determinant of A hat is determinant of k. This is determinant of A. So using some of those facts, fact number 1 and I guess the last one, so fact number 1 was if I multiply one row by k, then it is k times determinant of the matrix. And another one is I can decompose a matrix when we have something like this as the determinant of two matrices. And another fact was if two rows of a matrix are the same, then the determinant is 0. So using all those facts, the determinant of this 0, this decomposes into this, and this is 0 because of two facts, and then it just remains that. So this operation does not change the determinant. Now, what does this operation? What can this operation do? This operation can make this triangle 0, so it can give me an upper triangular matrix, right? So let's see. Let's check another operation, the last one, and see what it does. I'm not going to prove that one, but you can guess what happens and why the determinant is doing such a thing. So that's fact number 5. I guess it was fact 5. I don't remember. What is that? Well, I can remember. So the fact 5 is if I interchange a row, two rows, say, and I get matrix A hat, then determinant of A hat is minus determinant of A. So one interchange changes the determinant. You can guess because if in that expansion which I explained, there is a flip happening. There's a flip happening, and that flip changes the sign of each one of them. So the sign is like multiplying all of them by -1. Okay, so I'm not going to do anything here. About if you need to do this to find RREF, you're not finding RREF. In fact, you are just reducing using one row operation. But anyway, you might need this to make it simpler. That's okay. Just be careful when you do it one time. Just write somewhere on scratch paper that I did one flip. So in the end, you have to multiply the result by -1. Okay, let me think if there's anything else that comes into my mind. Oh yeah, and another one is this, fact 6, which is very simple. If I have a row or a column, if a row or a column of a matrix is all zeros, the determinant is 0. Determinant is 0. And you can guess how to prove this thing. Just use that row, use the cofactor expansion using that row. So when you do cofactor expansion using that row, it's all zeros times 0 times blah 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 blah, so you get 0. I can't recall anything else. If I need anything, any other facts, when I continue, I will write it for you at that moment. So, as I said, this row operation, the crucial row operation, which was row number I times k plus row j going to row j, does not change the determinant of it. Okay, so what can this do? And remember, just this row operation can give me a triangular matrix. So if A is whatever A is, this row operation gives me something like this. It's not A anymore, it is A hat 1 1 and 0, A hat 2 2. So this is A 1 1, A 2 2, A n n, and it's full. It's not 0. And then something da 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 da, and it is not 0. And then the third row will be 0 0 A hat 3 1 up to A hat no, what 3 1? This is 2 2. This is 3 3. And zeros. So the question is, what is the determinant of an upper triangular matrix? Upper triangular matrix. What is the determinant of an upper triangular matrix? Well, let's find it for a 3 by 3 matrix, okay? And for n by n is almost the same, so I'm not doing it, but you can, if you like, you can write down some proof for that. But it's interesting that the determinant of an upper triangular matrix is very simple. So, example, so this is upper triangular with A11, A12, A13, 0, A22, A23, 0, 0, A33. Let's using the first column. Okay, using the first column. Using the first column, I will get A11 times determinant of A22, A23, 0, A33. The determinant of this is this times this minus this times this. So it is A11, A22, A33. Now why I didn't write anything else? Because I'm using this column. So it is this times this, then 0 times something, 0 times something. So it is minus 0 times something plus 0 times something. I don't care what that is. I don't care what 0 is multiplied by, because 0 multiplied by anything is 0. So that's amazing. So the determinant of this is in fact just the product of the diagonal terms. Product of diagonal terms. So if I reduce a matrix using just that operation, just that one, and turn it into an upper triangular matrix, then the determinant of that matrix, the original one, is the product of the diagonal elements of diagonal terms of that upper triangular matrix. That's all. And you can guess this, you can just add this thing, then you will get 3 by 3, then, or n by n, n minus 1 by n minus 1, and so on. So I'm not going to do that. You can use this in induction, for example, to show that. But let me give you an example here. So let's say A is, let's just write 1 here, maybe 2, 5, say. Let's write 2. 0, let's say 8, maybe, and let's write minus 3 here. 1, negative, say, something, 6, maybe. Okay. So, I need 1 row operation, 2 row operations, and another row operation to get rid of this. So, 1 row operation is this, minus 2 times row 1 plus row 2 goes to row 2. And the other one, I have to get rid of this, 3 times row 1 plus row 3 goes to row 3. Okay, so let me do it here and change it over here. Minus 2, 4, minus 10, right? Minus 2, 4, minus 10 added to 2, 0, 8. I will get 0, 4, minus 2. So 0, 4, minus 2 will be the second row. And then 3 times that added to the third row. 3 times this one, 3 minus 6, 15, and then minus 3, 1, minus 6. So that's 0, minus 5, and that is 9, right? 0 minus 5, 9. Oh, gee, I erased the original matrix. Okay. I wanted to check with the original matrix. Okay, so this is not done yet. I have to get rid of this using this. And remember, I cannot divide by anything. Don't divide. So what row operation gets rid of this minus 5? So this should be 1, then times minus 5. So it is minus 5 over 4 row 2 plus row 3 goes to row 3, okay? So I need a minus 5 here, so this should be minus 5. How can I turn this into minus 5? Well, by multiplying minus 5, then divide by 4. So let's see what happens if I do this. So I will get minus 5 here. Then minus 5 times that is a minus 10, that's 10 over 4, which is 5 over 2, right? Yeah, minus, that's 5 over 2. Then I have minus 9 here, 5 here, and 9 here. So that's 0, and that is it positive? Yeah, positive. So 9, that is 18, 23. So, in the end, this is 0 and 23 over 2, 0, 0, 23 over 2. So, the determinant of this matrix A, this is not A anymore, this is like A hat, something. So, the determinant of A, which I erased, I shouldn't have done that, but anyway, so determinant of A is equal to determinant of A hat, and that is 1 times 4 times 23 over 2, which is, this is 2 for the unit 6. Okay. Now I cannot just go back, I cannot just rewind this thing, so you can go back and check. So let me see if there is anything else left here. Okay, so now let me, in the time that is left, I discuss some properties of determinants and some properties of determinants. Some properties if I multiply a determinant by by k, some constant, it's like multiplying each row by k, right? Row 1, row 2, up to row n. Determinant of that is k times a if it is just one row multiplied by k. Now I have n rows multiplied by k. So determinant of this thing is k to power n, determinant of a. And I wrote n by n, so we know that this n is the same. So that's number 1. Number 2 is determinant of a times b. That's interesting that the determinant is like this, acts like this. There's determinant of a times determinant of b. Okay, so now this has an amazing consequence. So number 3 is this. First of all, we know determinant of in is what? That is like an upper triangular matrix, right? It's like upper triangular matrix. So it is the product of the diagonal terms. What are diagonal terms of this? 1, 1, 1, 1, 1, 1. So it is 1. And number 4 is, now this one can give me determinant of these two, determinant of A inverse. So let's find the determinant of A inverse times A. This is I, right? So that's equal to determinant of I, which is 1, right? So determinant of A inverse A is determinant of I, which is 1. On the other hand, this guy here, this is also equal to determinant of A inverse times determinant of A. A inverse times determinant of A. Now, A inverse exists if the RREF of A, remember, A is n by n. Its RREF has no zero row. All of the rows are full. And when you turn it into RREF, all, say, because of that, all, say, diagonal terms are non-zero. All diagonal terms are non-zero. So the determinant of that matrix is not 0. So if A is invertible, its RREF has no 0 rows, which as a consequence of that, all diagonal elements are non-zero. Remember, if one diagonal element is 0, then it goes forward by something, at least one step. Then you will get a 0 row. So that was a theorem, in fact, I guess we proved. So A inverse exists. That's why I just wrote A inverse A. And also the determinant of A cannot be 0, as I said, because of that fact, because A inverse exists, this is not 0. So this equals 1, and this gives me a nice formula for determinant of A inverse, which is 1 over determinant of A. It's like the inverse is coming out of that formula, but it's not really that. But, you see, so determinant of A inverse is 1 over determinant of A. So these are like 4 of them. Let me check and see if there's anything that I am missing. And I also, the discussion I gave you here also gives me this fact. So let's write it as fact number 5. Fact number 5 is A n by n is invertible if and only if determinant of A is not 0. And remember I said this thing, the RREF of A has no 0 entries in its diagonal. Remember the RREF of A is something like this. You have something here with 1, well, the RREF is, well, not the RREF, let's, yeah, that's okay. So the RREF has all 1s in the diagram, right? And 0s here. So when I reduce it without using anything else, just that operation number 3, I will get that A hat, which has A hat 1, 1, say A hat 2, 2, and so on. A hat n, n, and 0 here and something here. Not 0. This one has 0. Not 0 here. So these are not 0. Can't be. If any of them is 0, then you will get 0 here. So none of them is 0. AI I is not 0 for any I. If AI is not 0, we know that determinant of A hat is determinant of A, so this can't be 0, because this is the product of these terms, so this can't be 0. So it's amazing. This is a nice check. So if you are given a simple matrix and you want to see if it is invertible or not, and it's easy to find its determinant, for example, then just do that. And if the determinant is not 0, then it is invertible. Let me see if there is another fact somewhere. Let me see here. Yeah, I gave the other fact to it. Yeah, also the inverse. I'm not going to write down the adjoint. Okay, Kramer's rule. So one thing remains, and that is Kramer's rule, which has a theoretical value. But let's solve a system, a simple system. So what's that? 1, 2, x2 is b1, a 2, 1, x1 plus a 2, 2, x2 is b2. Let's just multiply and add and blah, blah. So let's multiply this by minus a 2, 1. Okay, and I can multiply this by a 1, 1 and add. It's okay because I want to get rid of this. So I know that what I'm doing is changes some determinant, but that's okay. I just want to solve this thing. So I have minus a1, 1, a1, 2, a2, 1, sorry, a2, 1. A2, 1, x1 plus a 1, 2, a2, 1, and that's also minus. x2 is in minus a 2, 1, b1, and this will be a1, 1, a2, 1, x1 plus a1, 1, a2, 2, x2, and this side is A11, B2. So I add them as I will get this. So this stays. And when I add them, I will get this. I have A11, A22 minus A12, A21, X2, and that equals A11, B1 minus A21, B2. So X2 will be this nice guy. What is this? The denominator, you know, A11, A12, wow, this looks so familiar. That is a determinant of this. So whenever you see something like this, just think about determinants. The top one is also determinant. The top one is also determinant. But what is it? It's like expanding this. Wow, so the solution is in fact, this matrix is like this. This matrix, this system is A11, A12, A21, A22 times X1, X2 equals B1, B2. Okay? So what have I done? What happened? The denominator is the determinant of this coefficient matrix. The numerator looks like this, but the column corresponding to X2 is replaced with the right-hand side. So instead of the column, I replace that column with the right-hand side. And this is true for any system of equations which has n equations in n unknowns, the same number of equations as unknowns. So that is Kramer's rule. So let me write it. So if I have A n by n, x n by 1 is b n by 1, then x, say I, is the denominator is determinant of A, and numerator is determinant of AI. What is AI? AI is obtained from A by replacing its ith column with B. So the ith column of A is replaced with B. So AI looks like this. And column number 1, column number 2, column number I minus 1, then it's B, then it is column number I plus 1, up to column number n. See? So this is column I. Column I is replaced with B. And the determinant of that divided by determinant of A will give me a solution. Now, there are certain things that we can get from here. First of all, if determinant of A is not 0, I have unique solution. There is a unique solution. And if determinant of A is 0, then maybe there is a solution or maybe there is not. So that one depends. And we have to do something else. So determinant of A is crucial in knowing whether an n by n system has a unique solution or not. So that is a good check. Okay, so one conclusion is that if determinant of A is not 0, the system has exactly one solution. And remember, this is an n by n system. N equations with n unknowns. Okay, so I'm done with determinants, and next time I will start chapter 3, that's Euclidean spaces. That is the beginning of some deeper linear algebra. Especially chapter 4 is like a continuation of chapter 3 into dimension n. This one is dimension 3. If you have taken Calc 3, this looks familiar. Otherwise, it is a good start for Calc 3, in fact. So if you take Calc 3 in future, you will feel much comfortable at the beginning when you do lines and planes and things like that. Okay, so let me stop and see you tomorrow.